Hello there, this is Professor Eric Roldan. This video is for 13.4, which is about trees in graph theory. And so let's take a look at 13.4, and you're going to find these pages in your workbook. So let's get started. Well, all of you in some way or another have been exposed to family trees or organizational charts where there's a president and vice presidents or middle managers, employees, things like that. Government, you can look at organizational structure in the government. So basically, when it says create a family tree, this is exactly what we're going to do. So in reading this context here, we have Joe, and Joe has 2 children, Alan and Rosemary. And then it says that Alan has 3 children, so we're going to create 3 more branches of the tree. Chris, Danetta, and AJ. And Rosemary has also 3 children. Peter, Paula, and Martin. Okay? So this is a family tree, but this is also, in graph theory, a tree. Now, what we just created there in the family tree is a connected graph in which each edge is a bridge. Okay? So if we go back up to this, remember the definition of a bridge is that if you remove an edge in graph theory, in the graph, if you remove an edge, you create a disconnected graph or disconnected vertex. So if we remove, let's say, this one, then AJ has been disconnected. Okay, that vertex is disconnected. All right, so that's definitely a bridge. There's no way to get to AJ. If we take this one right here to Rosemary, then we're completely cut off from the family on the right side. Okay, there's no way to get there. Okay, so all of these are essential. Okay, all of these are essential. But with all of them there, we can all connect each person. Okay, we can connect them all. So that's what I mean by a tree is a connected graph in which each edge is a bridge. All right, so if you look, which of the following graphs are trees? Well, let me tell you a quick way to recognize something that's not a tree, okay? So if it's not a tree, if there is an edge, well, in reverse, that is not a bridge. And I'll simplify that in a minute. Okay, so a tree or a graph is not a tree if there is an edge that is not a bridge. So guys, a quick way to recognize that is if you see a polygon, there's going to be an edge that is not a bridge, okay? So if you take a look at these here, out of these 6, we see some polygons. Remember, a polygon is an enclosed figure. So a polygon is an enclosed figure in geometry. Okay, so the minimum I need to enclose this is 3 sides, right? So right now this is a tree, okay? But once I enclose it, now it's not a tree, okay? So if we see any polygons, no matter what shape they are, concave or convex or a bunch of sides or just 3 sides like a triangle, any type of enclosure is gonna indicate that it's not a bridge. So if we look, there's 3 polygons here. Okay, this one's the most obvious one that's enclosed. We got 2 polygons over here, 2 triangles, and we have one right here. Okay, there's that triangle right there. Which means if you remove one of those edges, you can still get to all the other vertices without any problem. So those are going to contain edges that are not bridges. So in conclusion, if you see some polygons, this is not a tree. This one's not a tree. And this one's not a tree. Now, why are the other ones trees? Well, there's no polygons, okay? No enclosure is created. So this one's a tree. Wait, this one, and this one. This one's a tree. And this one's a tree. Okay? Notice how all the vertices are connected, but there are no enclosures, no polygons in the figure. Okay? Okay, so there's a quick way to make this to make these not trees. If I enclose it right here, now it's not a tree. Okay? Or if I enclose it right here, now it's not a tree. Just a regular graph from graph theory. Or if I enclose it here, or here, or here, or here, okay? Any type of enclosure is going to indicate a polygon, which is not a tree. Okay, let's go to the next page and take a look at, we have a whole bunch of polygons here, but we can actually edit these graphs to make a tree, okay? And when we do that, it's called a spanning tree. So basically, when you create from another graph a tree by removing edges and things, then as long as they're all connected, then we've made a tree, okay? And so it's called a spanning tree because it's created from another graph. So like we're spanning the graph out to make a tree. We're spreading out all the edges. Okay, so if we take a look at this first figure on the left, we got to get rid of these triangles. So if I take this one out, this one out, this one, this edge, and this edge, if I take those 5 edges out, this is what's going to be created. So A, B, C, D, E, F, G. So the only thing that remains are the outside part. Okay? And that is a tree. Why is it a tree? Well, number one, there's no polygons. And number two, you can look and every single vertex is connected. Okay, we can get to every single vertex following the path. All right, there's no disconnected vertex, and so this is a spanning tree. We just created a tree from a graph that wasn't a tree. All right. Now here's another version of that same one. So what if I took out, let's see, that one, took out this down here for those triangles, and took out these two, then it would look like this. So, A, B, C, D, E, F, G. So notice how the B is connected to these three down here, and because I took those edges out in the bottom, it's no longer a triangle. And then go into C, and then just go to D, okay? So as you can see, there are no triangles, no enclosed figures, and they're all connected. So these are examples of trees, okay? So there's many more examples, just depending on how you create it. All right, let's take a look at this next graph over here on the right. All right, so let's create our 6 vertices, A, B, C, and then 3 down here, 2 in the middle. Whoops. Okay. All right, so tons of triangles there, lots of polygons. So what if we took out this one and this one and these two here, and those 3, and these right there. So I know it's a lot to keep track of. So what if I highlighted the path here so you can see it better? So let's say we start at G, then we go up to D, F, A, B, C, E, and H. As you can see, I made it to all the vertices, but it's not an enclosed figure. So if you take a look, started at G, went to D, F, A, B, C, H, and then E. So as you can see, we've connected all the vertices, but we did not create any enclosed figures, no polygons in this. Now, if I would have continued, then that would have created a polygon. That right there is a polygon. That doesn't count. It's not a tree. Or here, that's not a tree. Here, it's not a tree. There's a triangle there. So as long as we don't enclose the whole thing or even parts of it to make polygons, keep it open, all right, then this is going to be a tree, okay? So let's do another version of this. So set this up. Okay, so what if we made an X here. So let's take out this one, and these two here. So we'll make an X on the left side, and on the right side, let's see. So those 5 are connected. Now we can go to E or C, but I'm just going to go to C. Okay. Actually, we can go to both, as long as we don't enclose that. And then we can do from G to H. Okay. So basically, we made an X right here. Okay, that's not a polygon, so we're allowed to do that. And then we connected C to E, and then G to H. Okay, so notice that it is an open figure. There's nothing enclosed about it. These are all bridges, okay? Now, you can tell your graph is wrong if you have a rectangle in the middle, a triangle somewhere. Any of these triangles, it will be incorrect, okay? And then this right here is a weird polygon in the middle, but it's enclosed, so you can tell that that's incorrect, okay? So it's got to be completely open, but they're all connected. All right, that is a spanning tree, and I hope you take the time to maybe create your own from these two graphs. See if you can create a third example for each of these here. All right. Now let's get to the next topic, minimum cost spanning tree. So in the next section, now we're going to apply trees into finding the minimum cost. Okay, so it's very, very practical because this could be creating sidewalks or a path or all kinds of different ways. It could be travel. So we want to be able to have the minimum cost of whatever project that we're working with. So in this case, this is a triangle, all right? And there's different trees you can do with this. Okay, so the triangle is not a tree, but it is a graph. So you could do, you can connect A, B, and C like this. So that would be 23 and 17. Okay, that's a tree. Or you could connect these two as such. So it's going to be 23 and 48. Or you can create basically the right part of this. So that would be 48 and 17. Now, which one of those trees would be the cheapest? Okay, or the minimum, the smallest number. So these two basically, 23 plus 17 is 40. 23 plus 48 is 71. And 48 plus 17 is 65. So we have a winner, and that is this one over here. The first one we created is called the minimum cost spanning tree. In this case, okay, out of the 3 trees, it's the one with the lowest cost. Okay, if each edge has a particular weight or a number attached to it. Okay, so let's do some, let's go to the next page. All right, so in the next page, we have Kruskal's algorithm. And basically, again, algorithm is just procedure. A procedure to solve a problem. In this case, it has 3 steps. So it says, number 1, select the lowest cost edge on the entire graph. Okay, so if we look at this big graph here, our first step is to select the smallest one. Okay, which is, if you look, it is 11. All right, so that one's definitely gonna be created first. All right, then it says continue by selecting the lowest cost edges that do not form circuits. Again, do not try to do polygons. Okay, no polygons. So let's get this set up on the right. So you have 4 on the outside and then 4 in the middle. Okay. So what this is saying is go ahead and do from A to G. That's 11. Now, from G, we can go to either E or H or both. And if you look at the numbers, now you're going to compare. Okay, we're trying to get to the right side. And if you compare 47, 50, 53, 61, the lowest out of those 4 would be 47. Okay? So we can definitely get to H. Okay? Now we got to get to the middle somehow. And so if you look at how do we get to the middle? We have 38, 23, 48, and 57. And so we can choose the 23. Okay, so far so good. We still have a tree here. No enclosed figures. Okay, so let's get to the other vertices. Now, notice that this 71 here is really large, okay? But we don't need that 71. To get up to the top, we already have this 11 right here. So we're not going to draw this 71, okay? It's too big. All right. So let's choose between 31 and 62. 31 would be the smallest. This is going to get us to the top, or almost to the top. All right. Now, what's the cheapest way to get to D? Well, we can get to D through, let's erase all this. So we did these 3. So the cheapest way to get to D would be 53, okay, versus 62. All right. Okay. What's the cheapest way to get to B? So 61 or 57? Well, 57 is cheaper. So let's let's not use this guy and use 57. Okay, so we've pretty much made it to almost every vertex except for F, which I messed up right here. It's supposed to be an F. All right. So we have 3 ways to get to F. What are those 3 ways? We have 62, we have 50, and 48. Which one's the lowest? This 48. So that means we're gonna connect this way. That's 48. So if you look at all of our edges that we just wrote down here on the right side, these are the smallest numbers to get to each vertex. Okay, the smallest numbers. So this is a connected graph. There's no polygons, and we use pretty much the smallest numbers. Okay. Let's take a look at the next graph here at the bottom. Okay, so remember our goal was to get to every vertex. But getting there in the cheapest or smallest number way possible. Okay. Now, so how we're gonna start again. The algorithm wants us to start with the lowest. So if you look, the lowest will be this one. So we're definitely going to draw that over here. So let's label this A, B, C, D, E. Okay, so C and D are connected. Now, how do we get to E? What's the cheapest way to get to E? Well, if you look at our options, we have 3, 7, 4, and 8. So this one right here is the cheapest way to go to E. If that's the cheapest way, then we're not going to write any of these, okay? So we're going to cross these out and say, hey, we're going to get to E the cheapest way, which is 3. Okay? So now, all we have to do is somehow get to B and somehow get to C. Okay, so now let's take a look at B. What's the cheapest way to get to B? And if you look, we have 5 versus 19. Well, that's a pretty easy choice there. That 5 is the smallest. So we're going to connect those two. Okay. Now we cannot connect B and E because that'll create a triangle. All right, but we can try to get the C through B or through E. So which one's the cheapest? If you look, so between 19 and 4 is the cheapest way to get to C. So we're going to create that right here. And as you can see, guys, we've connected all of our vertices using the smallest numbers possible. And that is 1, 4, 3, and 5. Okay, that's the cheapest or the minimum cost spanning tree. Okay. Okay, so those are minimum cost spanning trees. Now let's apply that to a word problem on the right. The next page. So, an application. The Colorado Parks and Recreation Association wishes to build bicycle trails that connect the cities of Aurora, Boulder, Denver, and Inglewood. The approximate distance in miles between the cities are given in the table below. So again, we go back to our procedure of creating a weighted graph from the previous section, 13.3. We can tell that we have 4 vertices, so we can just create the same rectangle we've been doing all along. Okay, but we're going to do this on the left. So Aurora, Boulder, Denver, and Inglewood. Okay. So remember, you to complete the graph, this is a regular weighted graph, okay, not a tree. All right. And again, from our discussions, we don't have to do the whole graph. We just do the top half. So we're going to do 12. That's from A to B. We're going to do A to D is 14. A to E is 15. So we did that first row. Second row, B to D is 13. And B to E is 16. Okay, are we done? No, we still have one more side or edge to go, and that's going to be Denver to Inglewood. That's 26 right there. Okay. Okay, so this is the weighted graph like we did in 13.3. Now our job is to use Kruskal's algorithm to create the minimum cost spanning tree. So again, that means we need to go ahead and pick the smallest out of these numbers, which would be 12, or the lowest number. Okay, so we're definitely going to have A to B connected. Okay. Now, between between B and D, which one's the cheapest? Whoops. So to go down to D, to go down to the bottom half of the graph, we either go down 13 or we go down 15. And the cheapest way is 13. Okay? So we're going to do this one. We're going to do this one. Okay? So this was 12. This is 13. Okay? Now, what's the cheapest way to get to E? Well, what are our options? We have 16 that can get to E, 26 that can get to E, or 15 that can get to E. And the cheapest out of those 3 would be the 15. So we're going to go down. And there, we've connected all the vertices using the smallest numbers. Okay? So if we add these up, how many miles would this be? So 15 plus 12 plus 13. That's 40 miles. Okay. So there's the tree. The shortest distance would be 40 miles. Next question would say, okay, if it costs the bicycle trail $3,500 per mile to build, what's the total cost of building the whole bicycle trail from beginning to end? So all we're going to do is take our 40 miles times 3,500 for the cost per mile, and that's going to give us $140,000 for the total project. Okay. Okay, so this is using the concept of trees, particularly spanning trees, to create the minimum cost out of all of our options. We want to use the smallest numbers to connect all four vertices, and in this case it was 12, 13, and 15. Okay, and that created 40 miles of bicycle trail. 40 times 3,500, it's 140,000. So that is it for 13.4, guys, and we can talk more about this in class and start getting ready for the test, which is coming up. All right, see you soon. Have a great day. God bless.